Then how did you struggle?
We sat there. That's all I thought about. Well, I sat back there. I had to go to semester. I said, I can't do this.
I still understand how you feel, how you get back into your class. Because he's like,
I always kind of finish to our refrigerator. So I think they have to go after a while.
I have to see my tea, your key. I was supposed to keep it on train just now.
No, that's cool. Mark, keep it. I hope they put it in
So if I can do it, my math class, I've got almost an 8. It's like an 80, like an 8 or 89 CK. So, and then Shobi, I've got to get that though because I have struggles with that Shobi. I don't know if it's because I'm old, but that app just messes with me. Where you have to write on it, and you've got this little tiny space. It's just not working. And then I send stuff, and she says, I just can't write properly.
Yeah.
Yeah, they're the ones, I can tell you, the Shobis are the your terms. If you go on the book,
Okay.
it's on there. Everyone that says your
I did something a little bit different with the notes for chapter 15. And depending on if it works, that'll tell me whether or not I'm not, and whether you like it this way, then it'll tell me whether or not I want to do it in the future. Your notes are in D2L as they usually are. But this time, I also put the notes and the homework together in Shobi for chapter 15. So when you go to section 15.1 here, what you should find in your folder is both the chapter 15.1 notes, so that if you like taking your notes on your iPad, you can take your notes on your iPad rather than have to print them out in paper. And then I went ahead and posted PDFs of the PowerPoint so that if you miss class, you can open up the PowerPoint and download it and use that to take your notes. So if you like it that way, you can let me know that you do or you don't, or if you don't care one way or the other, that's okay. But you know, if you think this is a better way to do things, let me know. Because I'm trying to find a way to make things easier on you, especially since you have a blasted iPad anyway. You may as well get the maximum use out of it now that you've got it. But we are going to start section 15.1 today. And those notes are there. And I am going to record the lecture for 15.1. And if I can find a way to do it, I will post a link to the lecture and show you at 15.1 too. That way everything will be all in one place. So what we're going to talk about in 15.1 is taking derivatives and going back to what the function would have been before you started. Which means you really need to know how to take derivatives to do this. You've got to remember how you actually did it. And we're going to start with the easiest ones, which everybody in here is really good at because I've been giving you those quizzes and you're doing pretty well. Most everybody's making 4s and 5s on all those now. And I may put a couple more of them up in Shobi just to give you some extra quiz grades. But in 15.1, we're going to start out with the power rule and how you undo the power rule. So you have to remember, when we take the derivative of a function, and it has a power in several terms, what we do is we drop the power down in front and reduce the power by 1. If we have the result of that and we wanted to go backwards, we would add 1 to the power rather than subtract 1, and then divide by that new power rather than multiply, which is what we did to start with. You undo that by dividing by the new power. So that's where we're going to start. And your notes are, if you wanted to print them out, they are in D2L, but they're also in Shobi. Now you may be wondering, well, okay, you told me I got to learn to do this, but why? What's it good for? Well, it's good for a lot of different applications. Actually, integration is good for more applications in the real world than doing taking derivatives. I mean, it's nice to know the rate of profit is increasing, decreasing, and how fast. But a lot of times you don't have the information to come up with the function for your profit and your cost and your revenue to start with. But you can look at your revenue and see how it's changing over a period of time, which means you have the information to find the derivative of it, and then from there you could extrapolate back to what the original function was for your revenue. And the example I started out here is one that I gave in the book. It's actually a pretty good one. Consumption of energy generated by the wind, going to wind-powered energy, increased from just 70 trillion BTUs in 2001 to 1595 trillion in 2013, so over the course of about 12 years. So it really changed dramatically. Now, in between there, I'm sure they have data about how much it was in 2005 and 2008, and from there, they could look at the rate of the increase and determine what the derivative is, because they would have information to find a slope equation. What we want to do in this chapter is to estimate the wind consumption over the period of time using the definite integral, which is the end result of going backwards. And it's a concept that measures the area under a curve that would tell us the total amount that the use of wind energy has increased since 2001. But all we have right now is the rate of change that it increased by. So the same thing that allows us, like, for example, to determine the distance the cars traveled, if you've got its speed is a function of time. Its speed as a function of time is a rate of change. It's a derivative. And if I want to know where it was at any particular point in time from the time it started, I would need to know what its position equation was to see how far it had traveled. And scientists use it to determine how much a culture of bacteria is going to grow, and economists use it for how much consumers benefit by buying a product at the price determined by supply and demand, by looking at the rates of increase and decrease of both of those. So that's why we're going to learn to do this. So what we had, as I said, was in previous chapters, we would have an equation that told us about the total amount of some quantity, like cost or profit or revenue or temperature or gallons of oil or distance. And the derivatives of that information told us about the rate of change, how that quantity was changing over time. It allowed us to find things like your maximum revenue, your minimum revenue, your maximum profit, your minimum profit, when you reached a point of what we call diminishing returns, where your profit might be still increasing, but increasing at a much slower rate. But it's not always possible, like I said, to find those ready-made functions. You probably sat there a lot of times and thought, how in the world did they come up with that revenue function? How do they know that works? And the way they actually did it was they observed the revenue and how it changed over a period of time. And then they went backwards and found the function from the rate of change formula. So since the derivative gives us the rate of change when the total amount is known, the reverse of doing a derivative is called a process is a process called anti-differentiation. And the other word for anti-differentiation is integration. Integration means something totally different in mathematics from what it does in our normal everyday language. So our goal is to find an antiderivative, to reverse the derivative taking process. And we're going to make a little change in the notation. If we have a derivative, which we're going to call capital F prime of x, so that we're sure that, we're working on a derivative. And if the capital F prime of x is equal to f of x, then capital F of x is what's called the antiderivative of f of x. So if you have a rate of change, which is capital F prime, you can actually find the original derivative, its parent function, capital F of x. And here's your first example. If capital F of x is 10x, then f prime of x, capital F prime of x, is 10. So what that means is capital F of x is equal to 10x is the antiderivative of f of x equals 10. Now stop there for a second before you think about the other one. If you have a function and that function is 10x, what happens to capital F of x as x increases one more? How much does f of x increase each time x goes up by 1? If x is 0, then f of x is 0. If f of x is 1, capital F of x is 10. If x is 2, capital F of 2 is 20. How much is it going up each time?
10.
By 10. Is that 10 ever going to change? No. So does it make sense to you that that's why the derivative of that function is 10? Because that's a linear function. It has a y-intercept of 0 and a constant slope of 10. So its slope formula is just a number, okay? And its slope always stays the same, 10. And if you want to take it back to what is it the slope of, it's the slope of f of 10x. The x goes back in. Same thing with f of x is equal to x squared. Capital F prime of x is 2x. That's the derivative of capital F of x. That makes capital F of x equals x squared the antiderivative of 2x. You're taking derivatives and turning them back into what they came from. So I want you to think about now this is a derivative. What we have here is a derivative, and we want to find the antiderivative. What was it before we took the derivative? What did we take the derivative of to get this? Where did that 5 come from? Where did it used to live? Well, it used to be the exponent, right? But the exponent that's there right now is 4. Well, that's because I subtracted 1 from that exponent to get the 4. So I need to add 1 back to that exponent to get the 5 up there, right? So what I do then is a kind of a formula process. I take the n, the number in front, the coefficient, turn it back into the power, basically by putting it back up there where it's n minus 1. 4 is n minus 1 and 5 is n. So that means x to the 5th is the antiderivative of 5x to the 4th. What happens when you take the derivative of x to the 5th? What do you get? 5 comes down in front. X, reduce 5 by 1. 5 minus 1 is 4. 5x to the 4th. The good thing about integrals that you didn't have with derivatives, other than a trick or two I tried to teach you on the calculator, you didn't have any idea most of the time whether or not you were absolutely right. It was kind of hard to check yourself. But back in algebra days, when you had an equation, 2x plus 3 is equal to 7, you could solve that equation. You could solve that equation easily. You subtract 3 from both sides, then you divide both sides by 2, and you get an answer. But the best thing about that was you could plug the answer back in the equation you had to start with to make sure you were right. You haven't had that luxury with derivatives. That's been tough. Well, with antiderivatives or integrals, you do have that luxury. You can take what you get for an answer, cover up the derivative you started with, and take the derivative of your answer and see if it matches what you started out with. And if it did, then you know you did it right. So there is a check process in this, so that's good. Next example says, suppose we have a population in millions that's growing at a rate given by f of x is equal to e to the x, where x is the time in years from some initial time period. What kind of a function would give us the population itself at time x? Now, f of x is e to the x, and that's the derivative. What is e to the x the derivative of? E to the x. It's its own integral and its own derivative. The derivative of a function defined by capital F of x is e to the x, and its derivative is e to the x. So one possible function with that growth rate is capital F of x is e to the x. Notice I said one possible one, because there is a little hitch here. When we looked at 1b, where we had x squared, that was the parent function. Capital F of x was x squared, and its derivative was 2x. Well, it just so happens that g of x equals x squared plus 2 has that same derivative. Because 2 down in front, brought to power by 1, gives you 2x plus 2. Well, the derivative of 2 is 0. And h of x is x squared minus 4, has that same derivative, because its derivative is 2x minus 0, because the derivative of the constant is 0, and it disappears in the derivative process. And if you look at all three of these functions, they differ by exactly the amount of the constant, and that's all. All the constant does is move it up the y-axis or down the y-axis. So with those three figures, their tangent lines at any particular value of x are pretty much the same, except that they have different y-intercepts. Just like the functions themselves have different y-intercepts. So this is going to lead us to the fact that if you have two different parent functions that have the same derivative, the only difference between those two parent functions is some number c that's been added to the end of them, or subtracted from the end of them. So that means when we do an antiderivative, what we need to do every time so that we can specify that this is the derivative of any function that has this formula plus or minus some constant, is we need to put plus c. And I will tell you right now, my math lab will mark it wrong, and I will not give you the point. My math lab will mark it wrong if you don't put plus c on the end of it. Because that means you're recognizing this is the derivative formula for quite a few functions that are all different by a constant added or subtracted at the end. So this is called the power rule. for integrals. All of that leads us up to the power rule. You don't need to memorize this. You'll have formula sheets for the exam. The integral of x raised to a power is taken by adding 1 to its power and then divide by the new power. So this time you change the power first and divide by it, whereas when you were doing derivatives, you brought the power down first and then changed the power. This time you change the power first by adding 1, and then instead of multiplying by that, you divide by it. So let's look at some examples. And I have these in the PowerPoint, but my preference is to actually do them on paper to slow me down so I don't get ahead of you. So for the first one, you copy this one down. Oh, that pen's dead. The integral of t cubed, and dt tells you, or it's just kind of like an in-your-face reminder, by the way, that stuff in front of me, that's a derivative. Don't forget that's a derivative. So we're going to apply the rule. And here's what the rule says. It says add 1 to the power and divide by the new power. And then add what's called the constant of integration, which is just simply to say plus c. Okay? Is there any questions on that? This is the same process we're going to use for everything in this first part of the chapter. So the second one is the integral of 1 over t squared dt. And again, dt just means take the derivative. Now, I can't do this exactly the way that it is, because my power rule says it has to look like that. What is 1 over t squared equivalent to? That's right. This is equal to the integral of t to the negative 2 dt, and now I can take the derivative of it. Because I add 1 to the power and divide by the new power. And negative 1 plus, or negative 2 plus 1 gives me t to the negative 1 over negative 2 plus 1 gives me negative 1. So that integral is actually equal to negative, from this negative 1 in the bottom, 1 over t, if you want to change it back to that, plus c, or you could call it negative t to the negative 1. I don't have a problem with it, and my math lab won't have a problem with it if you don't make it back into a fraction. Either one is fine. So you can have it this way, or you could leave it this way. And either one works. Just don't forget the plus c. So then our next one says the square root of u du. And here again, I need to remember the things that I knew when I was doing derivatives. I've got to turn that into a power for the power rule to work. So this is going to have to be transformed into the integral of u to the 1/2 power du. And then when I take its derivative, that's going to be u to the 1/2 plus 1 divided by 1/2 plus 1. And 1/2 plus 1, if you don't remember fractions, your calculator does fractions, turns out to be u to the 3/2. And that's divided by 3/2. And if you add plus c, my math lab will take it that way. But an alternative way to do it is to remember if you're dividing by 3/2, you're multiplying by 2/3. And you can leave it as a power if you want to. Or, since that's a square root of u to the 3rd, and since u to the 3rd actually has a pair of u's that I can bring outside, if you do all the algebraic simplification, that's an equivalent answer. There's nothing wrong with this one. But if you want to give the others, you can. I want to see that first step. Show me the first step. Okay? Because it's in the first step I know you understood what you were doing. If somewhere between that first step and what you put down, you messed up something, I'm a lot more forgiving if I know you did the first step right. You might lose 1 point, you might not lose any. Because a lot of times when I'm doing grading your test, I don't even look past your first step. I look at your first step and say, yep, they did that right. So anything else you did after that didn't matter. I was really just looking at the first step. Okay, now we have the integral of dx. This one usually confuses the daylights out of everybody. Because they look at that and they say, okay, dx tells me whatever's in front of it's a derivative, but there ain't no derivative there. What the heck's going on? Why is there not a derivative there? What's always there if you can't see it? 1. But there's no x's. And I have a dx out there. What happened to the x's? What power of x is the same as 1? X to the 0 power. So as long as you've got the integral of dx, you know that what's sitting in front of it that you can't see because there's 0 of them is x to the 0 power. And now you can apply your power rule. Because your power says add 1 to the power, divide by the new power, and add a constant. So that means we've got x over 1, and x is to the first power, plus the constant. That's the only one that's kind of special. I hope I never have a class in this place, in this room again. I really do. Come on. about to hear Miss Flint get some really ugly language here in a minute. Okay. As I said, all the solutions are actually in the PowerPoint, but I'm working them on the side simply because it makes it slower for me, and that way you've got time to write everything down. Now, when we had a derivative of something like 2x to the fourth plus 3x, what did we do to take the derivative? Did we do it all in one fell swoop, or did we have to work with one piece of it at a time? We work with each term, right? Well, that's what we're going to do this time. There's also the fact, now, this rule, I'm going to be honest with you, this rule about the constant, you don't really need that rule. You really don't need that rule. It's okay, you can use it, you'll get the same answer either way. But until we actually have to have that rule, I'm not going to really say much about that rule. The other one, though, is simply saying that if you have the derivative of a bunch of terms added together and subtracted together, that the way that you do it is work on each term separately to do the antiderivative. And that's what we're going to do. So starting with the first example, we've got the integral of 2v to the third dv. What the power rule says is you add 1 to the power. Coefficients are a hitchhiker. They just ride along. Divide by the new power. Add the constant. So that means it's 2v to the fourth power over 4 plus the constant. And because 2 goes into 4 2 times, you can simplify it like that. Now all that power rule said, it gets you to the same place. All that constant rule said was that this is equivalent to taking that 2 outside and then doing the power rule. You're still going to wind up doing the same thing and coming out with the same thing. So that's why I said you really don't need that rule about being able to put the constant outside, at least not right now. If there comes a point where it'll come in handy, I'll tell you, but it's not really necessary. So then our next one is 12 over z to the fifth. And again, we're going to have to use the fact that that's in the denominator. We're going to bring it up to the numerator and change the power to a negative power. And then we're going to just bring the 12 along with us. Z to the negative 5 is going to be z to the negative 5 plus 1 divided by negative 5 plus 1. Add your constant. So that's 12 z to the negative 4 over -4 plus the constant. And -4 goes into 12 -3 times. Now, if you want to turn that back into a fraction, have at, but it's fine that way in my math lab. We'll take it with a negative exponent. Any questions so far? Anything you don't understand about the process so far?
Oh, yeah.
Not yet? Good. I usually get through the first section of chapter 15. People don't have too much trouble. It's when it's like, okay, maybe this is all right. I know what's wrong with it. You're waiting on the other shoe to drop, right? There's not any more to it than she's going to drop. She's going to drop something on her head in a minute. Not yet.
More papers here, I see.
Oh, yeah. Okay. Part C. Integral of 3z squared minus 4z plus 5bz. What the sum and difference rule says is you do each integral by itself. Okay. This one's going to be 3z to the 2 plus 1 over 2 plus 1 minus 4z to the 1 plus 1 over, oops, not z, 1 plus 1, plus, you got to remember, you can't see it, but it's there. Z to the 0 power is up there. So that's going to be 5z to the 0 plus 1 over 0 plus 1. And the only thing you have to do now is add one constant, because if you added a constant to all three of them, well, you don't know what the constant is. So when you add them all three together, you're just going to get a constant anyway. Since you don't know what it is, just put plus c. So 3 to the 2 plus 1 is 3z to the third minus 4z squared plus 5z, and your denominators are 3 and 2 and 1. 3 goes into 3, leaves you with just z cubed. 2 goes into 4 and leaves you with 2z squared. Plus 1 goes into 5, that gives us 5z plus c. And just, once again, to prove the point, this is a function. The derivative of this function is 3z squared minus 2 times 2 is 4z to the first power, which you don't have to write down, plus 5, 1 minus 1 makes the z disappear, plus 0, which we normally don't see, and that's the same as what we started with. So we know we did it right. So again, I'm gonna skip over the ones where I actually worked them out. And go on to something that's, looks like it might be a little more complicated. But it isn't, as long as you know the tricks. You've got the integral of x squared plus 1 over the square root of x. Now I'm going to be honest with you, there is another way to do that problem. But the easiest way to do that problem for us, knowing what we know, is to do it this way. And while I'm at it, I'm going to go ahead and write the other one down so I can go ahead and do it. So here's the first one. Since the power rule really isn't going to work well if I try to bring this up and call it x to the 1/2 power, because then I would have to try to multiply all this out, and I could do it that way, but that's a lot of trouble. What I want to do instead is I want to break this up. So that I can just concentrate on doing it one term at a time. Then I'm going to make my conversion back to powers. I've got x squared over the square root of x, which is x to the 1/2 power. And at this point, you need to remember your rules for exponents. If you've forgotten them before, now's the time you're going to have to go back and remember them. Remember, if you have a to the m over a to the n, you write that as a to the m minus n, top minus bottom. Okay? So I have x squared over x to the 1/2, which is going to be x to the 2 minus 1/2. This one I can just straight transfer back to calling it x to the negative 1/2 power. So then I'm going to actually do the integration at this point. 2 minus 1/2 is 3/2. But more importantly, I'm going to subtract 1 from the whole thing. So I may as well just leave it like that for right now and then use my calculator. And this is going to be x to the negative 1/2. I'm sorry, not minus 1, it's supposed to be plus 1. So there's the integration step. And now I'll use the calculator to get my fractions. That's going to be x to the 5/2 over 5/2. And negative 1/2 plus 1 is positive 1/2. And you can put that answer in and it'll check and it'll be just fine. If you want one that's easier to put in, you flip that 2 up in the top because you're going to flip 5/2 over and multiply by it. And I'm not going to put this over a 1 because it's kind of pointless. So there's your somewhat easier to type in answer. Now, if you ask them to show you how to solve one like that, they'll probably put the radicals back in it. I don't know. But I'm not going to bother with putting the radicals back in it, because it's the same answer either way. And then here's the last one. Now there is, again, another way to do this problem. Maybe, sometimes. But given the fact that this all I have is power rule, then what I'm going to have to do is I'm going to have to multiply out x squared minus 1 times x squared minus 1. Which, if you remember, when I gave you a chain rule power on the last test, I think at least 3 or 4 of you, where I gave you one that had a third power on it, you just took all 3 of those binomials and multiplied them all out, and then you took the derivative with power rule. Well, that works. So it works here too. So if I just go ahead and rewrite that, and then very carefully multiply it out. Don't make any mistakes. X squared times x squared is x to the 4th minus x squared minus x squared plus 1. Now that's easy to take the integral of, just using the power rule. It's going to be x to the 4 plus 1 over 4 plus 1 minus x to the 2 plus 1 over 2 plus 1 minus x to the 2 plus 1 over 2 plus 1 plus 1x to the 0 plus 1 over 0 plus 1 plus the constant out at the end. And yes, I know I could have put this together and call that minus 2x squared. But what you're going to see is you're going to get the same thing anyway. So I've got x to the 5th over 5 minus x to the 3rd over 3 minus x to the 3rd over 3 plus x plus c. And you can put these together at the end. Because if you were taking the integral of that single term, what you do is you would add 1 to the power. And then divide by the new power, which gives you negative 2x to the 3rd over 3, which is exactly what you've got here. So whichever way you see fit to do it is fine. Okay? Now we're going to come to the ones that you're saying, okay, this was easy so far. It's pretty straightforward. I can handle this. But you got to remember, you have exponential functions and logarithmic functions, and they involve powers. But the problem is the power is in the exponents. The rules are not terribly different. We already looked at e to the x. What I want to remind you of here, I'm going to write this down at the top and then show you. let's remember first how you take derivatives of exponential functions. The derivative of e to the x is e to the x. Okay, so the integral going backwards is still e to the x. The derivative of a to the x is 1 over the natural log of a times x. The x goes to the denominator. I'm sorry, it does not go to the denominator. My brain just loops. It stays in the numerator, just like e to the x does. It's the 1 over a, 1 over ln a. Now, the only difference in these rules that I'm showing you and those extra 2 that they're giving you is that sometimes you have an extra number floating around and it's in the power. And I'm just going to arbitrarily pick the number 3. Okay? The derivative of e to the 3x is e to the 3x, and then you would multiply it by 3. So if you have that constant there, the constant's going to wind up being a coefficient. Same thing here. That's going to wind up being a to the 3x and then going back to the rule so that you understand why it winds up where it does, it goes just like it does with e to the x, it goes to the denominator. Because you have to divide by it. Here you multiplied, but when you're doing the integral, you're going to divide by it. Here it is multiplied, but when we do the derivative, we do the opposite, so we're going to divide by it. Okay? So let's do a couple of examples, and that's probably, I think, the last of what we'll get done on this. And I'm going to do the first 2 in pairs so that you can compare them. Because they look very similar, but they're not. What you do on the first one is you carry the coefficient along with you and just take the derivative of e to the t. So what you wind up with on the first one is you do kind of do that constant thing. You bring that constant out front and ignore it for the time being. Then you just take e to the t dt. And the integral of e to the t is e to the t plus a constant. Now just bring your 9 down. So there's how that would work. But notice how different it's going to be when you have the 9 up with the power. Okay? Normally, if we were taking the derivative, not the integral, we would be doing e to the 9t times 9. But since we're undoing, we're not going to times 9, we're going to divide by 9. So you should compare those 2 answers and pay attention to where the 9 was and see how that they're very different from one another. One, you're going to keep multiplying by it, but if it's in power, you got to bring it down and divide by it. It doesn't follow the power rule, but it is a little similar to the power rule. I'm gonna pull these onto one slide so that you can see. Actually, I think I forgot to do the second one. Oh, no, it's there. So now you can look at both of them and see how it was different on that one slide. Now, going back to the other two, there's not a lot of similarities on those. You've got the integral of 3e to the t, or 3e to the 5-fourths u. du. I'm going to bring the 3 out front so I don't forget about it, but I don't want to be bothered with it while I'm trying to do this. So then the derivative of e to a power is e to the power. And then I need to divide by 5-fourths. But that's the same thing as multiplying by 4/5. So what I wind up with is 4e to the 5-fourths u plus c, and then all the way to the very end. I've ignored it up to this point, but I got to bring it back. Now I need the 3. And 3 times 4 is 12e to the 5/4u plus a constant. So it's a little bit different. Just remember, if there's something in the power, you're going to wind up with it with the denominator, not the numerator. Does anybody have any questions about that one? Because that one is different.
So how'd you get rid of the 4/5 again? How'd you get rid of 5?
Because what I did was, since this is divided by 5/4, then I flipped the 5/4 over and multiplied by it. So the 4, oh, thank you. Thank you. Good job.
Good job, Taylor.
4e to the 5-fourths u over 5 plus c, and then still have 3 times this. So it's 12e to the 5-fourths power, and it's over a 5. Thank you, Taylor.
Do you keep the U or does the U disappear?
No, the u stays. It was there, I just forgot to write down the last step. Yeah, she's paying attention. But then she always does. She's just better at catching me maybe than you are, Cody. Okay. Integral of 2 to the negative 5x. We're going to look back at the rule one more time, make sure you know why we're doing what we're doing. That fits the form of a to a k times x integral. And the way we do it is we keep a to the k times x, but we divide by the constant and we divide by the natural log of the base. And there it went again. The hardest part is making it put this little ring light back on. I think it switches that stuff.
really not too. I think Rachel.
I'm sorry, for me it is too. Okay, fine, we'll go back to the PowerPoint. We've only got one left. So what we did, the base is 2. We take the natural logarithm of 2 and divide by it. We keep 2 to the minus 5x in the numerator, but because there's a minus 5 coefficient in the numerator, we bring it down in the denominator and divide by it. You don't change it, you just bring it down. Okay? Now there's one exception. The power rule works for any power of x except 1. And that's -1. X to the -1 does not work with the power rule. The power rule completely and absolutely and utterly fails you, and I'm going to show you why it would. If I tried to use the power rule on that, here's what would happen.
No, that's what it does. You have one. And it's divided by 0, which is 9. Look at me.
Why can't we do it?
Can't divide by 0.
That's right, you can't divide by 0. So we have to have a different approach. Hopefully you will remember that the natural logarithm of x's derivative is 1 over x, which is x to the -1. Okay? So that tells us if we have x to the -1, the antiderivative is the natural logarithm of x. Now the absolute value bars are there because you can't have x to be negative. Can't take the natural log of negative numbers. It has to be positive. But the truth of the matter is that becomes redundant because when you apply powers to it, it's not going to be negative anyway. So it's there. Like for example here, if you took the natural log of x squared plus 1, well, it doesn't matter. You square x. If it's negative, it becomes positive. If it's positive, it's still positive, and add 1 to it just makes it more positive, so it's still going to be able to be something you take the natural log of. So x squared can't ever be negative anyway, so you don't have to worry about that. So that means that we can do a problem like this one. 4 over x is exactly the same thing as 4 times 1 over x. So take the 4 out front and just let it hang out for a while. And the antiderivative of 1 over x is the natural log of x. And then bring the 4 back down with it and add a constant to it. And then if you've got -5 over x, that's the same as 5 and the negative sign, so -5 times the integral of 1 over x, so just the integral of 1 over x is the natural log of x, put the negative 5 back in front of it, you have its integral. And then the second term is e to the negative 2x. Well, the integral of e to the negative 2x is e to the negative 2x. And it's divided by 2, so they chose to call it 1/2, but I would have been fine if they had written that out as e to the negative 2x minus e to the negative 2x over 2, and that's just the same thing. So I would have skipped the pulling the fraction out front part. There was no need to do that. Now, it is possible, I've got 3 minutes left, so I'm going to tell you it is possible, but I'm not going to beat you up over it right now. It is possible to figure out what the constant is. So when we come back on Thursday, I will pick up at example 9. And we'll talk about that, and we'll review how to do the integrals a little bit at that point, because I know you probably are going to spend your time working on the test, which I have right here. They review on Thursday at the beginning of class. Which means, no, I don't expect you to have your chapter 15 section 1 homework back. Although I would suggest that you set aside a few minutes and look at the show me problems while this is still fresh on your mind. Just a minute. So if I will note to myself.